Every star you have ever seen is a furnace burning at millions of degrees, and yet the space around it is the coldest place that exists. And over the next couple of hours, we'll find out how both of those things can be true at once. Today, we'll travel from the surface of the sun to the empty dark between galaxies, looking for the reason the universe is freezing while everything in it is on fire. If this feels like your kind of place, subscribe. Let's begin. Hold a number in your mind for a moment. Minus 270 degrees Celsius. That is the average temperature of the universe. Not of some distant, forgotten corner of it, but of the whole thing, measured in every direction we point an instrument. It is barely 3 degrees above the coldest temperature that is physically possible, and it is the temperature of a universe that is absolutely full of fire. There are somewhere near 2 trillion galaxies within reach of our telescopes. Each one holds 100 billion stars, give or take, and every one of those stars is a sustained nuclear explosion that has been burning for millions or billions of years. The sun alone burns through 4 million tons of itself every second. Its core sits at 15 million degrees. Point a telescope anywhere at all and you are looking at furnaces stacked behind furnaces all the way to the edge of what we can see, and the space holding all of it is colder than anything you have ever touched. This is the contradiction we are going to live inside for the next couple of hours. Everything is burning. Space is freezing. Both measurements are correct, taken with the same instruments, on the same night. A thermometer floating between the stars would read close to absolute zero, while the light of 10,000 fires passed straight through it without warming it at all. If that sounds impossible, it should. It violates something you have known since you were small. That fire is warm, that standing near a flame makes you warmer, that the closer you get to something hot, the hotter you become. In space, almost none of that holds. You can float in raw, unfiltered sunlight and freeze. You can be surrounded by stars and feel nothing from any of them. The full answer to how this works is going to take the whole night to assemble. It lives in the strange machinery of how heat actually moves, in the almost unimaginable emptiness between things, and finally in something about the universe itself that was only discovered by accident by 2 men who were certain their instrument was broken. We'll arrive there near the end. For now, sit with the strangeness of it. You live on a warm, wet rock, wrapped in a thin layer of air that traps and shares heat so generously that you almost never think about it. It is one of the only places in the known universe where warmth behaves the way your body expects it to. Step off it in any direction and the rules change. The sun is 93 million miles away, and it keeps you alive. Move a little closer and it could kill you in seconds. Move into its shadow just behind a wall of metal and you would begin to freeze while the same star blazed a few feet away. To understand why, we have to start with a question that sounds almost too simple to ask. A question children ask and physicists struggle to answer cleanly. What is temperature actually? Because it is not the thing you think it is. Temperature feels like a thing an object has. The way it has a color or a weight. A cup of coffee is hot, an ice cube is cold. The hotness seems to live inside them, waiting to be felt. It doesn't. Temperature is not a substance. It is a measurement of motion, specifically the average speed at which the tiny particles inside something are jittering and bouncing around. That is all it has ever been. In the hot coffee, the water molecules are racing, slamming into each other and into the walls of the cup billions of times a second. In the ice cube, the same kind of molecules are barely shuffling, locked into a slow crystal. Heat is movement. Cold is stillness. When you warm your hands over a fire, what is really happening is that fast-moving particles are crashing into your slower ones and speeding them up. The warmth you feel is a transfer of motion, nothing more. This is why absolute zero, minus 273.15 degrees Celsius, is a floor that nothing can fall below. It is the point where the jittering would stop completely, where particles hold perfectly still. The universe never quite reaches it, but it comes astonishingly close in the empty dark, far closer than anything you will ever encounter on Earth. Here is the part that quietly breaks the everyday idea of temperature. If motion is heat, then temperature only means something when there is something there to move. A single particle alone in a vast emptiness traveling extremely fast is technically very hot, and yet it carries almost no heat at all because there is so little of it. Speed is not the same as quantity. Picture two rooms. One holds a single bullet, fired fast enough to glow. The other holds a warm bath. The bullet is moving far faster than any molecule in the bath, so by the strict logic of temperature, it is hundreds of times hotter. But step into that room and you would not feel warm. You would feel nothing until the bullet hit you. The bath, full of slow, crowded, gently moving molecules, holds vastly more heat, even though each one moves at a crawl. That gap between how fast things move and how much heat they actually carry is the first key to the whole mystery. Space, it turns out, is full of particles moving incredibly fast. It is also nearly empty, and those two facts together will let it be technically blazing and genuinely freezing in the very same place. You can almost feel the shape of the answer forming, but it rests on the second word in that sentence, the one we have been using loosely all along. Nearly empty. We say space is empty the way we say the desert is dry, as a kind of rounding. The truth is stranger and far more extreme than the word can hold. To understand why a thermometer freezes between the stars, you first have to understand how little is out there to touch it, and almost nothing in your experience has prepared you for how much nothing there is. Let's try to build the emptiness honestly, because the usual words fail at it. Start with the air in the room around you. It feels like nothing. You walk through it without resistance, and most of the time you forget it exists. Yet every cubic centimeter of that nothing, a space about the size of a sugar cube, holds roughly 25 quintillion molecules. That is a 25 followed by 18 zeros in a volume you could balance on a fingertip. They are packed so densely that each one travels only a tiny fraction of a millimeter before colliding with another. Now go up. In low Earth orbit, where the space station flies, that same sugar cube volume holds maybe 10 billion particles. That sounds like a lot, until you remember we started in the quintillions. Already the air has thinned by a factor of more than a billion. Keep going. Out past the planets, into the space between the sun and the nearest stars. Out there, that same sugar cube volume holds about one atom, sometimes less. A single, lonely hydrogen atom, drifting with empty distance in every direction before it might meet another. Let that settle for a moment. The air at your desk, 25 quintillion particles in a thimble. Interstellar space. One, to find a second atom, that lonely hydrogen would have to travel, on average, several centimeters. An ocean, at its scale. This is the truth the word empty is trying and failing to carry. Space is not mostly empty. It is empty with rare, almost accidental exceptions. if you shrank the sun down to a single grain of sand and set it on a table, the next grain of sand, the nearest star, would not be across the room. It would be in another city, and that is one of the more crowded neighborhoods in the galaxy. Now bring a thermometer into that picture. To read a temperature, it needs particles to strike it, to transfer their motion into its molecules. On Earth, 25 quintillion of them hammer its surface every instant, and it warms or cools almost immediately to match. Out between the stars, it might wait minutes, even hours, before a single atom drifts close enough to touch it. The fires are still out there, the stars still burn at millions of degrees, but the messengers that would carry that heat, the crowd of moving particles, are simply absent. The furnace is real. The room it would warm has almost nothing in it to be warmed, and so the strangeness deepens instead of resolving. The emptiness explains why nothing carries the heat from atom to atom out there, but you might object, and you would be right to, that the sun clearly does reach us across that same emptiness. You can feel it on your skin on a clear morning, 93 million miles from the source, so heat does cross the void somehow. It found a way to reach your face this morning without any particles to carry it. There is a second method of moving heat, and it is the only one the universe can use across the dark. It is also the slowest and the strangest of the three. There are exactly 3 ways heat can move from one place to another. Once you can see all 3, most of the mystery of cold space stops being a mystery and starts to feel almost obvious. The first is conduction. This is heat moving by direct contact, particle to particle. Touch a metal spoon left in a hot pot, and the burn travels up the handle into your fingers as fast molecules jostle their slower neighbors down the line. Conduction needs a crowd. It needs things touching things, passing the motion along like a rumor through a packed room. In a vacuum, with nothing touching anything, conduction simply stops. There is no chain to pass the heat down. The second is convection. This is heat carried by a moving fluid, warm air rising off a radiator, hot water circulating in a pot, the churning that makes a whole room evenly warm. Convection needs a substance that can flow and carry its heat somewhere else. It needs air or water or some medium in bulk. In the near vacuum of space, there is no fluid to rise, nothing to carry warmth from one place to another. Convection dies for the same reason conduction does. There is nothing there to do the carrying, so 2 of the 3 ways heat moves are useless in space. Both of them depend on matter, on crowds of particles touching and flowing, and matter is the one thing the void does not provide. This is the deep reason the emptiness matters so much. It does not just thin the heat out, it switches off 2 of the only 3 mechanisms that move heat at all. That leaves the third, and it is the strange one: radiation. Not the dangerous kind from reactors. Radiation here just means energy traveling as light. Every warm object glows whether you can see it or not. Your own body is glowing right now in infrared, pouring heat into the room as invisible light. A heat lamp does the same in wavelengths you can almost feel. The sun does it across the entire spectrum, blazing in light from radio to gamma, and light does not need anything to travel through. It crosses pure vacuum perfectly happily at 300,000 kilometers a second. This is the one method of moving heat that works in space, the only way the fire of the stars reaches anything at all. So the sun does warm your face on a clear morning, and it does it by radiation, by light crossing 93 million miles of near-perfect emptiness and striking your skin. Conduction and convection had nothing to do with it. There was nothing out there to conduct or convect through. This is why an astronaut can float in full sunlight and still be in terrible danger from the cold. Radiation only warms the side facing the light. There is no air around them to spread that warmth, no medium to even it out. One cheek can be baking while the other freezes, with no way for the heat to travel around. To feel how violent that split really is, it helps to stop talking about thermometers and astronauts in the abstract. It helps to put you out there in a suit with the sun on one side of your body and the dark on the other. Leave the room behind for a moment. Let the floor fall away and the air and the comfortable evenness of a planet that shares its heat. Put yourself in orbit 300 kilometers up in a white suit facing the sun. On the side of your body turned toward it, sunlight is arriving with nothing in its way. No atmosphere to filter it, no clouds, no haze. The outer surface of your suit there climbs toward 120 degrees Celsius, hot enough to boil water nearly half again over. That side of you is in a furnace. Now notice your other side, the one facing away toward open space. There is no sunlight there. There is also no air to carry any warmth around from the bright side. That surface is radiating its heat straight out into the dark and getting nothing back, and it falls toward minus 100 degrees. The same suit, the same instant, 200 degrees of difference across the width of your shoulders. This is not a thought experiment. It is the actual engineering problem that kept spacewalks impossible until it was solved. The suits astronauts wear are threaded with water tubes that constantly move heat from the hot side to the cold, doing by machine what air does for free on Earth, spreading warmth around so that no part of you cooks while another freezes. Without that quiet circulation, a human body in vacuum would be a thermal disaster, baked and frozen at once. Turn slowly and watch what happens. As you rotate, the line between scorching and freezing sweeps across your body like a tide. There is no warm middle ground, no gentle gradient of pleasant warmth fading to cool. There is light and there is its absence, and almost nothing in between. On Earth, step from sun into shade, and the air around you keeps you company. The temperature barely flinches. Here, the shade is 200 degrees colder, and it begins the instant the light stops. Look down at the earth beneath you, that blue curve wrapped in its thin white veil of air. Everything that makes warmth feel normal, the way a room stays evenly heated, the way a cloudy day is still survivable, the way night cools slowly instead of all at once. All of it comes from that fragile layer. It is a heat-sharing blanket only a few dozen miles thick, and you have just stepped off the edge of it. Out here, the sun is not a source of comfort. It is a directional blade of energy that scorches whatever it lands on and abandons everything it does not. The cold is not an enemy arriving from somewhere else. The cold is simply what the universe is, in the absence of a fire pointed directly at you. And this brings up a question with a beautifully ordinary answer, one you have been holding in your kitchen your whole life without knowing it. If the problem of space is that heat cannot travel without matter, then what would happen if you deliberately built a small piece of space here on Earth? A pocket of engineered emptiness designed to trap warmth by refusing to let it move. Someone did exactly that more than a century ago. You have almost certainly held his invention in your hands. In 1892, a Scottish physicist named James Dewar was wrestling with a stubborn problem. He worked with gases cooled until they turned to liquid, oxygen, and later hydrogen at temperatures hundreds of degrees below freezing. The trouble was keeping them cold. Heat from the warm laboratory kept creeping into his samples and boiling them away before he could study them. His solution was to fight heat by removing the things that carry it. He built a glass container with double walls, and then he pumped the air out from the gap between them, leaving a thin shell of vacuum wrapped around the inside. Heat from the room could no longer conduct across that gap, because there were almost no particles in it to pass the warmth along. It could not convect across, because there was no air to flow. He had cut off 2 of the 3 ways heat moves on purpose in a vessel small enough to sit on a bench. To handle the 3rd way, radiation, the heat that travels as light, he silvered the glass like a mirror so that any warmth arriving as infrared light was simply reflected back instead of soaking in. Conduction blocked. Convection blocked. Radiation bounced away. Inside, his liquefied gases could rest in the cold for hours. You know this object. The vacuum flask he invented is the thermos in your kitchen, the one that keeps coffee hot through a long morning and ice water cold through a hot afternoon. Every one of them is a small, deliberate piece of outer space, a manufactured emptiness whose entire job is to stop heat from traveling. When your coffee stays warm for 6 hours, it is because the heat cannot find a crowd of particles to escape through. It is trapped by the same nothing that freezes the void. There is a quiet irony folded into this. The thermos keeps things hot by surrounding them with a little vacuum, and the great vacuum of space keeps everything cold for the very same reason. The mechanism is identical. The emptiness does not care whether the warmth is on the inside trying to get out or on the outside trying to get in. It simply refuses to carry heat across itself in either direction. A vacuum is not warm or cold by nature. It is an insulator, and an almost perfect one. This is the hinge the whole mystery turns on. We tend to imagine cold as something that flows in, an active force creeping toward us through the dark. It is not. Cold is only the absence of moving heat, and space is cold because it is the best insulator that exists, a place where the fire of the stars, real as it is, simply cannot find a way across to warm anything that is not standing directly in its light. Which leaves one question still standing, the one that should have been bothering you this whole time. If space is such a perfect insulator, if heat can barely cross it at all, then how does any of the sun's warmth reach us down here? How does a fire 93 million miles away, separated from us by the most perfect emptiness in nature, manage to warm a single human face on a clear morning? The answer is that the sun cheats. Using the one method that needs no crowd and no medium, it sends its heat as light. Deep in the sun's core, where the pressure is unimaginable and the temperature reaches 15 million degrees, hydrogen is being crushed into helium, and that fusion releases energy. The energy works its way outward over thousands of years until it reaches the surface and leaps free as light across the whole spectrum, from the radio waves we cannot see to the visible glow that lights our sky to the ultraviolet that burns skin. That light pours out in every direction at once, and a tiny sliver of it, a vanishingly small fraction, happens to be aimed at Earth. It crosses 93 million miles of vacuum in about 8 minutes and 20 seconds, untouched, because vacuum is exactly what light crosses best. Then it strikes the top of our atmosphere and the air and the ground and your skin, and only there, when it finally lands on something made of crowded particles, does it become heat again. The light was not warm in transit, it was just energy traveling. It became warmth at the moment it was absorbed. This is the loophole the stars use to be felt across the void. Conduction and convection were dead out there, killed by the emptiness. Radiation slips across the gap precisely because it does not need anything to slip through. The sun does not warm the space between us and it. That space stays at its terrible cold even as the light streams through it, because light passing through a vacuum has nothing to deposit its energy into. The warmth only appears at the destination, on the first solid, crowded thing the light strikes. Stand outside on a clear winter morning and you can feel this directly if you pay attention. The sunlight on your face is warm. The air around you might still be cold. The ground frosted hard. The light is not heating the journey. It is heating you, the surface it lands on. Step into the shade. Put a wall between yourself and that one specific fire, and the warmth vanishes at once, even though the air temperature has barely changed. You have just done in miniature what the astronaut did rotating in orbit. You moved out of the light, and the universe's true temperature reasserted itself. Everything depends then on standing in the path of a fire. And this raises a problem of distance, because that beam of starlight does not stay strong as it travels. The sun feels powerful from here, but here is a specific distance, and that distance is doing more work than you might think. The same fire that could cook you from too close would leave you freezing from too far, and the line between those fates is drawn by a simple, merciless piece of geometry. It is the reason a campfire warms your hands from a step away and does nothing at all from across a dark field, and it scales all the way up to the stars. Picture a campfire on a still night. Stand close, palms out, and the heat is almost too much. Take one step back and it eases. Walk several steps into the dark field, and the fire becomes something you see but no longer feel. A bright point that warms nothing. The fire did not get smaller. It is burning exactly as hot as before. What changed is how its warmth is spread out. The light and heat leave the fire in all directions, expanding outward as a growing sphere. Close in, that energy is concentrated on a small surface. Farther out, the same amount of energy is smeared across a vastly larger sphere, and so any one patch of it, your hands, your face, receives only a thin slice. The mathematics of this is unforgiving, and it has a name: the inverse square law. Double your distance from a fire, and you do not get half the heat. You get a quarter. Triple the distance and you get a ninth. Move 10 times farther away and the warmth reaching you drops to 100th of what it was. The energy falls off with the square of the distance every time for every source of light and heat in the universe. Now scale the campfire up to a star and the field up to a solar system. The sun is a fire of incomprehensible size. size, but the inverse square law treats it exactly like the campfire. Earth sits at a distance where the sun's spread out warmth happens to be just right, enough to keep oceans liquid, not enough to boil them. We did not choose this. We simply formed at a radius where the fire feels gentle. Move inward toward Mercury, and the same sun becomes a hammer. Mercury is about 2.5 times closer to the sun than we are, and so it receives roughly 6 or 7 times the sunlight, enough to heat its dayside past 400 degrees Celsius, hot enough to melt lead on the ground. Move outward, and the warmth drains away with terrifying speed. Mars, only half again as far from the sun as we are, already receives less than half our sunlight, and its summer noon struggles to climb above freezing. By the time you reach Jupiter, 5 times our distance, the sun delivers about 1/25 of the warmth it gives Earth. Out at Saturn, it is closer to 100th. The fire never changed, only the distance did, and space gives you distance in amounts the human mind was never built to hold. Not steps across a field, but hundreds of millions, then billions of kilometers, each one thinning the warmth by the square. This is why the cold wind's almost everywhere. The fires are rare and fixed in place, and the distances between them are so vast that their warmth is diluted nearly to nothing before it reaches the next thing that could feel it. There is a place in our own solar system where you can watch this dilution reach its bleak conclusion, where the sun, our sun, the one that scorches Mercury, shrinks to something you could almost mistake for an ordinary star. Let's go there. Leave the inner solar system behind, past Mars, past the asteroid belt, past Jupiter and Saturn and the pale rings, out to the small frozen world of Pluto, nearly 40 times farther from the sun than Earth is. Stand on Pluto's surface and you would need to imagine standing, because at minus 230 degrees Celsius, the nitrogen in its thin air has frozen onto the ground as frost, and the warmth of your body would be the most violent thing for miles. Look up for the sun. It is still there. It is still, by far, the brightest object in the sky. But it is no longer a disk you cannot look at. It is a brilliant point of light, a star slightly too bright to stare at comfortably, casting shadows thin and sharp across the ice. This is high noon on Pluto. The sun is at its highest, the day as bright as it ever gets. And it is roughly the brightness of a heavily overcast afternoon on Earth, or the moment just after sunset when the first streetlights flicker on. People have a name for the light at this distance. They call it Pluto time, and you can look up when the sun will fall to that exact dimness over your own house some evening, then step outside and stand in it. That fading dusk, that almost dark, is the brightest day Pluto will ever know. Now feel for the warmth of it. There is none. The inverse square law has done its full work across that distance. Pluto receives roughly 1/1600th of the sunlight Earth gets. The same fire that melts lead on Mercury that warms your face in July arrives here as light without heat, a bright memory of a star. You could stand in Pluto's full noon sunlight forever and never feel a trace of warmth from it. This is the strangeness made visible. On Mercury, the sun is a destroyer, hot enough to melt metal. Here, the very same sun is a cold lamp, a thing you see but cannot feel, and the difference between those two worlds is nothing but distance. The same star, viewed from 2 seats in the same enormous theatre, and Pluto is not even close to the edge. It only marks the rough boundary of the planets. Beyond it, the sun keeps shrinking through the comets of the outer dark until eventually it would dwindle to just another star among the thousands. bright perhaps, but hard to pick out at a glance from the others, its warmth long since spent into nothing. And yet the sun is not finished with the dark, even out here. It is not only sending light outward, it is breathing, exhaling a thin, ceaseless wind of its own substance that streams past Pluto and keeps going, carving out a vast bubble in the surrounding galaxy. We live deep inside that bubble, all of us, and almost nothing humanity has ever built has reached its edge. The sun does more than shine. It leaks. From its blazing outer atmosphere, a steady stream of charged particles flies off in all directions at hundreds of kilometers a second, a thin, constant gale called the solar wind. It blows past the planets, past Pluto, far out into the dark, and it does not simply fade. It pushes back against the thin gas of interstellar space and inflates an enormous bubble around the entire solar system, a bubble we call the heliosphere. We live inside it, every human who has ever lived, deep within this shell of the sun's own breath. It stretches far beyond the planets, more than 100 times the distance from Earth to the sun, before it finally meets resistance. Out at that edge, called the heliopause, the sun's wind loses its push against the gas between the stars, and the bubble ends. That boundary is, in a real sense, the true edge of the sun's domain, not where its light ends, which is essentially nowhere, but where its breath finally stops. Only 2 objects built by human hands have ever crossed it. The Voyager probes, launched in 1977, flew past the outer planets and kept going, and after 35 years, the first of them, Voyager 1, finally pushed through the heliopause in 2012 and entered true interstellar space. For the first time, something of ours was outside the bubble, in the raw gas between the stars, sending back word of what it found. And what it found returns us to the strange lesson about heat. The gas just outside the bubble is, by temperature, blisteringly hot, hundreds of thousands of degrees, in places over 1 million. By the strict measure of how fast its particles move, Voyager had flown into a furnace. Yet the probe did not melt, did not even warm. The gas is so unimaginably thin, so close to perfect vacuum, that those scorching particles strike the spacecraft far too rarely to deliver any real heat. Voyager's danger out there was always the cold, never the heat, slowly freezing in the dark, not burning in the million-degree gas around it. This is the same trap we keep walking into, dressed in new clothes. 1 million degrees and it would freeze you. The temperature is real. The warmth is absent, because warmth needs a crowd. And out there the crowd is gone. So we live in a warm pocket, inside a vast bubble, inside a freezing galaxy. The sun's light fills the bubble. The sun's wind shapes it, and beyond its edge, the true cold of interstellar space waits, technically blazing, genuinely frozen. But step back far enough and a different question starts to press. If the universe is so full of fire, 2 trillion galaxies, each with 100 billion suns, fires stacked behind fires in every direction we look, then why, when you go outside at night and tip your head back, is the sky overwhelmingly, almost completely dark? With that much fire in every direction, the night should blaze. It does not. And the reason it does not is woven into the same answer we have been chasing all along. It is one of those questions that seems too simple to be deep, until you sit with it. Why is the night sky dark? Here is why it should not be. Imagine the universe is infinitely large and filled more or less evenly with stars in every direction going on forever. Then no matter where you looked, any point in the sky at all, your line of sight traveling outward would eventually land on the surface of some star. Close stars, far stars, unthinkably distant stars, but always eventually a star. Every single point in the sky would end on a burning surface. The entire night sky should be a solid sheet of fire, as bright as the surface of the sun, in every direction at once. There should be no night at all. This puzzle is old enough to have a name. It is often called Olbers' paradox, after an astronomer who wrestled with it 2 centuries ago, though others asked it before him. And the simple fact that the sky is dark, that there is night at all, was a genuine clue about the nature of the universe, hiding in plain sight, available to anyone who ever looked up and wondered. The resolution is the same machinery we have been building toward all night. First, the universe is not infinitely old. It had a beginning about 13.8 billion years ago, and light travels at a finite speed, so we can only see as far as light has had time to reach us in that span. Beyond a certain distance, there are surely more stars and galaxies, but their light has not yet had time to arrive. The fire is there, the messengers are still on their way. Our view ends at a wall, not of darkness, but of unfinished journeys. And second, the deeper reason the universe is expanding, stretching the light of the most distant things until it cools out of visibility entirely. The farther away a source is, the more its light has been stretched on the way here, sliding from visible glow toward infrared, toward microwave, toward wavelengths your eye cannot catch. The most distant fire of all has been stretched so far that it no longer looks like fire, so the night sky is dark, not because the universe is empty of fire, but because it is young enough and stretched enough to hide most of it, and the darkness is not even truly complete. If your eyes could see microwaves, the entire night sky would be glowing evenly in every direction, a faint hiss filling every gap between the stars. That is the thing worth holding onto as you drift. The blackness overhead is not truly black. It glows faintly everywhere with light too red and too cold for human eyes. The stretched out remains of an ancient fire. The dark has a temperature, and it is almost exactly the temperature our lonely thermometer kept falling to, far from every star. So, what is that temperature really? Where does this even all-directional warmth come from? The floor beneath all cold, the glow that fills the dark. We have circled it all night. It is time to name it directly. Take that thermometer to the most isolated place imaginable. Not just the edge of our solar system, but the deep space between galaxies, where the nearest star is thousands of light years off, and the combined light of every fire in the sky is too faint to register. Let it sit there, far from everything, for as long as you like, shedding its heat into the dark. It will fall, and then it will stop. At about 2.7 degrees above absolute zero, minus 270.4 degrees Celsius, it holds steady and goes no lower. No matter how far you carry it from every star, the cold has a floor, and the floor is not zero. Something is warming it. Faintly, evenly, from every direction at once, a whisper of energy is arriving and holding it those few degrees above the absolute bottom. Turn the thermometer any way you like, toward a galaxy, away from one, into the blackest gap in the sky, and the floor is the same. Whatever this warmth is, it is not coming from any single fire. It is coming from everywhere, the same in all directions, soaking the entire universe in a uniform, almost imperceptible heat. This is the temperature of space itself. Not the temperature of any object in it, but the background level that everything settles to when left alone, the thermal hum of the cosmos. And it took us until 1965 to find it by accident, and at first we were certain it was a mistake. Hold on to that number to 2.7 degrees, because it is the answer the whole night has been circling. That faint, even warmth is the thing that keeps the universe from ever quite reaching absolute zero, and where it comes from is the resolution of our entire paradox. We will follow it all the way back to its source before the end. For now, notice only what it tells us about cold. The universe does not let things fall to absolute zero, even in the emptiest void there is. It holds them a few degrees above, gently. Everywhere there is a faint fire that has no single location, a warmth with no campfire and no sun, and it fills all of space at exactly the same temperature. It also tells us something humbling about the dark we have been describing. When you imagine the gaps between the stars as perfectly empty and perfectly black, you are very nearly right, but not quite. The whole of that darkness is glowing, ever so slightly, with a light too faint and too red for your eyes to catch. The emptiness is not truly empty. It has a temperature, it has a glow, and both are almost, but not entirely, nothing. Before we can follow that whisper of warmth back to where it began, we have to deal with a confusion that has been lurking underneath everything we've said. We keep using the word hot and the word cold as if they were opposites of the same thing. They are not. There are places in this solar system that measure thousands of degrees and would still freeze you solid. And until that makes sense, the rest never will. Here is a fact that sounds like an error. 200 miles above your head, in the layer of the atmosphere called the thermosphere, the same region where the space station orbits, the temperature can climb past 2,000 degrees Celsius, hotter than molten lava. And if you were floating there unprotected, you would not burn. You would freeze. Both things are true. And the contradiction lives entirely in that slippery word, hot. Remember what temperature actually measures: the average speed of particles. Up in the thermosphere, the few particles that exist are moving extraordinarily fast, energized by raw sunlight. Each one, individually, is screaming along at a speed that corresponds to thousands of degrees. By the strict definition, the gas is blisteringly hot. But recall the lonely thermometer between the stars and the difference between speed and quantity. The thermosphere is so thin, so close to vacuum, that those fast particles are spread incredibly far apart. A few of them might strike your body each second, far too few to deliver any meaningful warmth. Meanwhile, your own body is radiating heat away as infrared light, pouring it into the surrounding dark far faster than the rare, fast particles could ever replace it. The gas is technically thousands of degrees. The heat it can actually deliver to you is almost nothing. This is the distinction that untangles half the confusion about space. Temperature is how fast the particles move. Heat is how much energy actually gets transferred, and that depends not just on speed, but on how many particles there are to do the transferring. A sparse gas can be enormously hot and carry almost no heat. A dense, slow substance can be cool and carry a great deal. You already know this in your kitchen, even if you have never named it. Open a hot oven set to 200 degrees and reach your bare hand into the air inside. The air is 200 degrees and you can hold your hand in it for a few seconds because air is thin and carries little heat. Now touch the metal rack at that same 200 degrees for even an instant. The metal is dense, packed with particles ready to dump their energy into your skin, and it burns you immediately. Same temperature, wildly different heat. The number on the dial was never the whole story. So when we say space is cold, we are making a careful claim. It is not that there are no fast particles out there. In places near stars, the sparse gas can measure thousands or even millions of degrees. It is that there is so little matter spread so thin that almost no heat can be delivered to anything at all. You would freeze inside a cloud measured at 1,000,000 degrees because the cloud, for all its speed, has almost nothing in it to warm you with. This is the trap that nearly every instinct about heat falls into. And nowhere is the trap more spectacular or more genuinely unexplained than at the sun itself, where the temperature does something that, after more than half a century of looking, we still cannot fully account for. You would expect the sun to be hottest at its core and to cool steadily as you move outward, the way a campfire is fiercest at its heart. For most of the way, that is exactly what happens. The core sits at 15 million degrees. The visible surface, the layer we see as the bright disk, has cooled to around 5,500 degrees Celsius, still searing but far less than the core. So far, so sensible. Then something happens that should not. Just above that surface lies the sun's outer atmosphere, the corona, the faint pearly halo you can see during a total eclipse. And the corona is hotter than the surface beneath it, not slightly hotter. It blazes at 1 to 3 million degrees, hundreds of times hotter than the surface it sits on top of. Sit with how strange that is. It is as though you walked away from a campfire out into the dark field and found the air getting hotter the farther you went from the flames. The heat source is the core. The surface is cooler than the core, as expected, and then past the surface, away from the source, the temperature leaps back up by a factor of several hundred. The energy seems to skip the surface and deposit itself in the thin gas above, and for a long time no one could say how. This has a name. It is called the coronal heating problem, and it is one of the oldest open questions in the study of the sun. We have leading suspects now. Tangled magnetic field lines knotted by the sun's churning may snap and reconnect, dumping vast energy into the corona. Waves of magnetic and plasma motion may ripple up from below and break like surf in the thin outer gas. Spacecraft like the Parker Solar Probe have flown closer to the sun than anything we have ever built, diving through the corona itself to measure it from the inside. But I want to be honest with you, here in the dark, because this is not a place that pretends to certainty it has not earned. We do not fully know. We have strong ideas and good data, and the answer is probably some combination of the magnetic explanations. Yet the clean, complete account, the one that closes the case for good, we do not have it yet. One of the most studied objects in the entire sky, the star we have watched longer than any other, is doing something with its heat that we cannot yet completely explain. And notice, even here, the lesson from a moment ago holds. The corona is millions of degrees, yet it is so thin, so close to vacuum, that the total heat it holds is modest compared to the dense surface below. It is the perfect demonstration of the difference between temperature and warmth, written across the face of our own star. Searingly hot, barely substantial, We have followed heat from the kitchen to the corona now. We have seen why it cannot cross the void by touch, only by light, and how that light thins to nothing across distance. But there is one more place. The everyday idea of heat collapses completely, and it is the one closest to home. It is the reason the second planet from the Sun is hotter than the first. Mercury is the closest planet to the Sun. By every instinct we have built tonight, it should be the hottest place in the solar system. It sits in the full hammer of that nearby fire, receiving up to 11 times the sunlight Earth does, and its day side does climb past 420 degrees Celsius. Hot enough to melt lead, as we said. But Mercury is not the hottest planet. The hottest planet is Venus, the second one out, farther from the Sun, receiving only about a quarter of the sunlight that falls on Mercury, and its surface holds steady at around 465 degrees Celsius. Hotter than Mercury's blazing noon, hot enough to melt lead everywhere, all the time, day and night, pole to pole. The reason is the very thing space does not have, the thing that makes warmth behave normally anywhere it exists. Matter. Venus is wrapped in a colossal atmosphere, about 90 times thicker than Earth's, made almost entirely of carbon dioxide. That dense blanket does two things at once. It traps the sun's heat, letting light in and refusing to let the infrared warmth radiate back out, a greenhouse effect run to a catastrophic extreme. And because it is a thick, churning fluid, it carries that heat everywhere by convection, spreading it across the whole planet so evenly that even the long Venusian night never cools. Mercury, by contrast, has almost no atmosphere at all, barely more than the vacuum around it. So Mercury behaves the way space taught us things behave. Its day side scorches under direct radiation, and its night side, with no air to hold or carry the warmth, plunges to minus 180 degrees. The same world swings nearly 600 degrees between day and night because it has no blanket of matter to even things out. Venus, smothered in air, barely changes temperature at all. This is the whole lesson of the night, written across two neighboring planets. Heat needs matter to be held, to be carried, to be shared. Where matter is thick, like Venus, warmth pools and spreads and lingers, and a planet farther from the fire roasts hotter than one closer in. Where matter is thin, like Mercury, heat strikes and flees, and the same surface bakes and freezes within a single rotation. And where there is almost no matter at all, in the open void, heat can barely exist as usable warmth at all. It only passes through as light, on its way to the next rare, crowded thing. Your own planet sits in the gentle middle of this. Earth's atmosphere is thin enough not to smother us like Venus, thick enough to share warmth and soften the night. Unlike Mercury, we live in a narrow band where matter is balanced just well enough that heat behaves kindly. It is worth remembering how rare that balance is. Almost nowhere else does warmth treat its inhabitants so gently, and yet even where the fire is fiercest, the cold finds places to hide. There are spots in this solar system that sit close to the sun, bathed in its fury, and hold ice that has never once melted. Ice that may be billions of years old, sitting a few steps from blazing rock. On the Moon and on Mercury, the planet closest to the Sun, there are craters near the poles whose floors have not seen sunlight in billions of years. Because these worlds barely tilt, the Sun never climbs high at their poles, and the deep floors of certain craters lie in permanent shadow, their rims forever blocking the light. Sunlight rakes across the surface nearby, heating it to hundreds of degrees. A few kilometers away, down in the shadow, the temperature has not risen above minus 170 degrees for as long as the craters have existed. And in that permanent cold, there is ice, water ice, frozen solid, sitting in the dark on the surface of Mercury, a world whose sunlit ground is hot enough to melt lead. The two extremes share the same small planet, almost within sight of each other, the most blistering rock in the solar system, and pockets of ancient ice the sun's fury has never once touched. How is that possible, so close to the fire? It is everything we have learned made local. The sunlit ground is hot only because the light lands directly on it. Move into the shadow where no light reaches, and there is almost no air on Mercury to carry warmth around from the bright side. No convection, barely any conduction across the near vacuum. The cold floor cannot borrow heat from the blazing rim. It radiates away what little warmth it has into the black sky overhead and gets nothing back. It is a piece of deep space, preserved at the bottom of a crater an arm's length from a furnace. This is the astronaut in orbit again, the one cheek baking while the other froze, written into the crust of a planet. Light and its absence, side by side, with no medium to blur the line between them. On Earth, ice could never survive beside heat like that. Our air would carry the warmth into the shadow within minutes and melt it away. Mercury has no such mercy, and so the ice endures, sorted from the fire by nothing but a wall of rock and the rules of how heat moves. There is something quietly astonishing in it. The closest planet to the sun is also in its hidden corners, one of the better places in the inner solar system to find ancient ice. The fire and the freezing do not just coexist across the vast distances of space. They coexist within a single crater, a few kilometers apart, each held in its separate state by the same physics that freezes the void. And this is the exact problem that anything we send into space must survive. Not heat alone, and not cold alone, but both at once, swinging between them with nothing in between. The bright side cooking, the dark side freezing, and no air to share the difference. A human body cannot survive it unaided, neither can a delicate machine. So how do our probes endure decades out there, on worlds that would bake them and freeze them in the same hour? The answer is that we learned to send them out carrying their own small fires. The first lesson came the hard way, on the surface of Venus. In the 1970s and early 80s, the Soviet Union landed a series of probes there, the Venera landers, the only machines ever to touch that surface and send back pictures. They worked beautifully for a little while. In the crushing pressure and the 460-degree heat, the longest any of them survived was about 2 hours before the heat killed it. We have a handful of photographs of the Venusian ground taken by machines that were dying as they took them. The outer solar system poses the opposite threat. A probe sent to Jupiter, Saturn, or beyond receives almost no warmth from the distant sun and would freeze solid, its fuel lines, its electronics, its instruments cracking in the cold long before it arrived. Sunlight is far too weak that far out to power it or to warm it. Something else has to keep it alive. The solution is to give the spacecraft a fire of its own, probes bound for the deep cold carry what is called a radioisotope thermoelectric generator, a block of plutonium that, as it naturally decays, produces a steady, gentle heat for decades. That warmth is converted into electricity to run the instruments, and it also keeps the spacecraft's vital parts from freezing. The probe carries, in effect, a tiny, slow, artificial star in its belly, enough to hold off the cold of the outer dark for 30, 40, even 50 years. This is what keeps the Voyagers alive, out past the edge of the bubble, in interstellar space. Each one runs on the slow heat of decaying plutonium, and that is the clock now ticking down on their lives. The plutonium fades a little every year, producing less warmth and less power, and one by one the spacecraft have been shutting down their instruments to save what heat remains. They will not die because something strikes them. They will die because their small fire finally goes out, and the cold they have held at bay for half a century at last gets in. There is something deeply human in this picture. Out in the most hostile emptiness there is, our machines survive the same way we always have. By carrying a fire, by huddling around its warmth, by rationing it carefully against the dark. The Venera landers had no fire that could outlast the heat, and they died in hours. The Voyagers carry theirs still, and have lived for decades. The difference between them is the difference between everything alive and everything cold, a source of heat, held close, kept burning as long as it possibly can. And it works only because the fire is right there inside the machine, warming it directly. Step even a small distance away and the warmth would be useless. Which brings us back to the cruelest fact of all about the dark, the one we have circled but never quite faced. The fires of the universe are not just rare. They are separated from one another by distances so enormous that no warmth could ever pass between them. To feel how enormous, we have to shrink the whole thing down until it fits in the palm of your hand. Let's build a model of the galaxy small enough to hold. Take the sun, that furnace 1,000,000 times the volume of Earth, hot enough to vaporize anything that approaches, and shrink it down to a single grain of sand, a tiny speck 0.5 millimeter across resting on your fingertip. At that scale, where is the Earth? It is a mote of dust far too small to see, drifting about 5 centimeters away, 2 finger widths from the grain of sand. The entire orbit of our planet, the whole vast circle we travel in a year, fits within the span of your open hand. Everything you have ever known, every human who has ever lived, every war and ocean and city happens on an invisible speck 2 finger widths from a grain of sand. And the next grain of sand, the nearest other star, Proxima Centauri, it is not on the table, it is not in the room. At this scale, the nearest star is another grain of sand more than 400 meters away, 4 city blocks, with nothing in between but bare table. 2 specks of sand 400 meters apart, and that is one of the closer stellar neighbors we have. Between them, emptiness, almost perfect and almost total, the freezing dark we have been describing, scaled down to a 1/4 mile of nothing separating 2 0.5 millimeter grains. Now feel what that means for warmth. Each grain of sand is a fire, but the second grain is 400 meters away. Could you possibly feel the heat of a single grain of sand from 400 meters off? Of course not. You could not feel it from 4 centimeters. The inverse square law has drowned its warmth in distance 1 billion times over before the heat travels a fraction of the way. Each star sits alone in an ocean of cold, its fire pouring out in every direction and reaching essentially nothing before it fades to nothing, and this is only 2 stars. To hold the whole galaxy at this scale, you would need to scatter grains of sand, a few 100 billion of them, across a region the size of a continent with hundreds of meters of emptiness between neighbors, and the whole thing slowly turning in a dark that goes on between the grains almost forever. That is our galaxy. That is what full of stars actually looks like when you measure the space around them. Mostly, overwhelmingly, it is the space. So when we ask why space is cold, the grain of sand gives the simplest possible answer. The one underneath all the others. The fires are real and they are fierce, and there are uncountably many of them, but they are scattered so unimaginably far apart that almost everywhere you are too distant from every single one of them to feel a thing. The universe is not cold because it lacks fire. It is cold because it is mostly the distance between fires, and yet not every scrap of warmth in the dark comes from a star. There are worlds out in that cold that are not waiting on any distant fire. They make their own heat from the inside, and a few of them may be the likeliest places to find life in the entire solar system. We have treated the sun as the only fire that matters, the single source every cold world depends on. For most of them it is. But not all warmth in the universe is borrowed from a star. Consider Jupiter. It sits 5 times farther from the sun than we do, receiving a small fraction of our sunlight, and by rights its weather should be driven entirely by that distant warmth. Yet when we measure carefully, Jupiter radiates almost twice as much heat as it receives from the sun. Some of its warmth is its own. The planet is so massive that it is still slowly contracting under its own gravity, and that slow squeeze generates heat in its depths, leftover warmth from its formation, and the steady pressure of its own enormous weight. Saturn does the same. These giants glow faintly with an inner heat that has nothing to do with the sun. The strangest cases are the moons. Far out by Jupiter, the small icy moon Europa is wrapped in a shell of frozen water, locked in a cold that should have stilled it forever. But Europa is squeezed and stretched by Jupiter's immense gravity as it orbits, kneaded like dough, and that constant flexing heats its interior. Beneath the ice, warmed from within, there is thought to be a liquid ocean. More water, perhaps, than all of Earth's seas combined, kept liquid not by sunlight but by the friction of a tide. Saturn's little moon Enceladus does the same, and we have watched it spray plumes of water from cracks at its south pole, jetting into space from a hidden warm sea. Sit with what that means. Out in the deep cold, hundreds of millions of kilometers past the comfortable zone where the sun keeps water liquid, there are oceans. Dark oceans, sealed under ice, never once touched by sunlight, kept warm by the slow grinding of gravity. And when we ask where in the solar system, beyond Earth, life might most plausibly be hiding, these are the places we name first. Not the sunlit worlds, but the cold ones, with a private fire burning inside, warming a sea that has never seen a star. It is a quiet correction to the whole picture. Warmth in the universe usually comes from the fires of stars radiated across the void to whatever happens to lie in the path. But gravity can make heat too by squeezing, and so a few cold and distant worlds carry their own faint warmth in their hearts, independent of any sun. The same principle that warms Jupiter from within is, in a sense, the same one keeping the Voyagers alive, a fire carried inside against the dark. Still, all of these inner fires are small and temporary and rare. They warm a handful of worlds in an ocean of frozen ones. The overwhelming truth of the universe remains the cold, and if you go looking for the very coldest place in it, you will not find it in the empty gaps between the stars. You will find it somewhere stranger, a place colder than the background of space itself. Colder even than the leftover fire of the universe, which should not be possible at all. We have said all night that the universe has a floor 2.7 degrees above absolute zero, and that nothing left alone in the dark falls below it because the faint glow of the early fire keeps everything that little bit warm. For the empty gaps between the stars, that is true. The background warmth sets the temperature and there it stays. But there is a place that is colder. About 5,000 light years away lies a young, dying star surrounded by an expanding cloud of gas it has flung off in a structure called the Boomerang Nebula, and inside that outflowing gas, astronomers have measured a temperature of about 1 degree above absolute zero, nearly 2 degrees colder than the background of space itself. As far as we know, it is the coldest natural place in the entire universe. Colder than the deepest void, colder than the leftover fire, the single chilliest spot we have ever found. How can anything be colder than the background everything else rests at? The answer is a piece of physics you have in your kitchen, run in reverse. When a gas expands rapidly, it cools. This is why an aerosol can feel cold after you spray it, why compressed air blown out of a nozzle chills your hand. The dying star at the heart of the boomerang is hurling its gas outward extraordinarily fast, and that gas is expanding so violently that it cools itself below even the temperature of space, the way a spray can cool below the temperature of the room. It is a natural refrigerator, light years across, chilling itself by sheer expansion faster than the background fire can warm it back up. It will not last. As the gas slows and spreads, the faint warmth of the cosmos will creep back in, and the nebula will drift up toward 2.7 degrees like everything else, settling onto the universal floor. For now, though, there is a patch of the sky colder than the dark around it, a place that has briefly, locally, beaten the background fire and dropped closer to absolute zero than the void itself manages. There is something almost poetic in where the true cold turns out to live. Not in the empty nothing, as you might expect, but right beside a star, in the dying breath of a sun. The fire and the freezing, once again, found in the very same place, the coldest spot we know of, made by the death throes of a furnace. Even at the extremes, the two are never as separate as they seem. And notice what holds the floor for everything else. We keep returning to it. That 2.7 degree glow, the warmth the boomerang has to outrun, the heat that keeps the void from absolute zero, the hiss in a New Jersey antenna, the dark that is not quite dark. It has been the quiet center of every answer all night. It is time, finally, to follow it all the way back, to the moment it was born, and to the two men who heard it first without understanding what they had found. Because before we knew what the universe was made of, they sat in the cold with a strange and stubborn sound, certain their machine was broken. In 1964, in a quiet corner of New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were trying to do something very ordinary. They had a large horn-shaped antenna built to study faint radio signals from the sky, and before they could use it, they needed to account for every source of noise, every hiss and crackle that was not the thing they wanted to measure. There was one hiss they could not get rid of. A faint, steady static, the same no matter where they pointed the antenna, up, down, at the horizon, at empty sky, by day or by night. It did not come from any city, any star, any single direction. It was simply there everywhere they looked, a whisper of microwave energy soaking the whole sky evenly. They tried everything to make it go away. They checked their equipment for faults. They suspected the antenna itself, and when they found that pigeons had been roosting inside the horn, leaving droppings on the metal, they cleaned it out thoroughly and removed the birds. The hiss remained. The static was not a flaw in the machine. It was real, and it was coming from the sky itself, from every part of it at once. What they had stumbled onto without looking for it was the temperature of the universe, that 2.7-degree warmth arriving as faint microwave light from every direction, the same flaw beneath the cold that our imaginary thermometer kept settling to. They had not set out to find it. They thought for months that it was noise to be eliminated. It turned out to be one of the most important measurements ever made, the faint heat of the cosmos itself, and it won them the Nobel Prize. There is something quietly moving about how this discovery arrived. Not in a triumphant search, but as an annoyance. A hiss two men spent months trying to silence, cleaning birds out of a horn in the cold New Jersey air. The universe was handing them its oldest light, the warmth left over from its very beginning, and at first they only wished it would stop. And it is genuinely the oldest light there is. That microwave glow has been traveling untouched for more than 13 billion years. Far longer than the Earth has existed, far longer than there have been eyes to catch it. When it began its journey, there were no stars yet, no galaxies, no planets. It set out across a universe that looked nothing like ours, and it has been arriving, faint and even, ever since. To understand why that ancient warmth fills all of space, why it is the flaw beneath every cold thing, the reason no thermometer can fall to absolute zero, we have to ask where it came from. And the answer overturns the entire picture we have been building, because we have spent this whole time treating the universe as a cold place dotted with rare fires. There was a time when it was the exact opposite. A time when the entire universe, every cubic inch of it, was the fire. Run time backward. Take everything that exists, every galaxy, every star, all the matter spread across all that emptiness, and pull it back together. As the universe contracts in reverse, everything crowds closer, and as it crowds, it heats. Compression is heat. Squeeze any gas and it warms. Run it back far enough and the entire universe becomes dense and brilliant and impossibly hot. About 13.8 billion years ago, in the first moments after the beginning, there was no empty space dotted with fire. There was only fire. Every point in the universe was filled with a searing, uniform plasma. Particles of matter and light packed together so tightly and moving so violently that the whole cosmos glowed at thousands, then millions, then unthinkably higher degrees. There were no stars because the universe was hotter than any star. There were no cold gaps between things because there were no gaps. The fire was everywhere and it was everything. In that state, the universe was not even transparent. Light could not travel freely. It bounced between the densely packed particles like a shout lost in a crowd, never crossing the room. The whole cosmos was an opaque, glowing fog, the same in every direction, a fire with no outside and no edge. Then the universe did the one thing it has never stopped doing. It expanded. Space itself stretched, and as it stretched, all that packed matter and light spread out and thinned and, exactly as our campfire taught us, cooled. The same law that drains the warmth from a fire across a dark field was now operating on the entire universe at once, but in time rather than in distance. The fire was not going out. It was being pulled apart, spread thinner and thinner across a growing volume, growing cooler with every passing age. After about 380,000 years of this, blink against the billions to come, the universe had cooled just enough. The plasma thinned and calmed until, for the first time, light could travel freely without being battered between particles. In a single cosmic moment, the fog cleared. The universe became transparent, and the light that had been trapped inside the fire was suddenly set free to fly across the opening dark. That light is the hiss Penzias and Wilson could not silence. It is the 2.7-degree glow our thermometer kept settling to. It is the released flash of the universe's own fire, the moment the cosmos turned clear. And it has been traveling through space ever since, in every direction, for 13.8 billion years. But that light left when the universe was thousands of degrees hot. The glow we measure today is a freezing 2.7 degrees. Something cooled that ancient fire by a factor of more than 1,000 on its way to us. And it was not distance, and it was not any blocking matter. It was the stretching of space itself, still happening, still pulling the old fire thinner with every second that passes. And once you see how, you see the whole answer at last. Light is a wave, and a wave has a length, the distance from one crest to the next. That length is what your eye reads as color. Short waves look blue and violet. Longer waves look red, longer still, and the light leaves visible sight entirely, becoming infrared, then microwave, then radio. The wavelength is the light signature, and it carries the light's energy. Short, tight waves are energetic and hot. Long, stretched waves are weak and cool. Now remember that space itself has been expanding this entire time. Not things flying apart through space, but space itself growing, the distance between everything quietly increasing. And here is the crucial part. When a wave of light travels through space that is stretching, the wave stretches with it. Its crests are pulled farther apart, its wavelength grows, the light reddens and cools, simply because the space it is crossing keeps getting larger beneath it. The fire's light left the early universe as a fierce glow, the light of a furnace at thousands of degrees in short, hot wavelengths. For 13.8 billion years it has been crossing an expanding cosmos, and all that time its waves have been stretching, lengthening, cooling. By now they have been pulled out more than 1,000-fold, stretched so far that the fierce visible glow of the early fire has become faint microwaves, the wavelength of a cool, even hiss. The fire did not go out, its light was stretched until it froze. This is the answer the whole night has been assembling. The 2.7 degree temperature of space, the floor beneath all cold, the warmth that keeps every thermometer from reaching absolute zero, is the light of the universe's original fire, cooled by the expansion of space from thousands of degrees down to a few degrees above nothing. The cold of the cosmos is not the absence of the fire. It is the fire still here, still arriving from every direction, stretched and dimmed almost to silence by the swelling of space across unimaginable time. So, the universe is cold because it is old and because it is growing. It began as fire with no room, and it has spent 13.8 billion years giving that fire room, more and more of it, until the same flame that once filled every point now barely warms the dark to 3 degrees above the bottom. Every star you see is a small, late rekindling, a place where gravity gathered the thinned-out matter and lit it again. But the background, the true temperature of everything, is the old fire, very nearly spent. The paradox dissolves, and what is left in its place is something close to grief and close to awe. When you feel the cold of space, you are not feeling the absence of warmth. You are feeling the first fire of the universe, stretched so thin across so much time that only a whisper of it remains. And the stretching has not stopped. Space is still expanding, faster now than before, which means the old fire is still cooling, still dimming year by year toward a future that is colder than anything that has ever been. Let yourself drift forward now, the way you drifted back, not 13 billion years into the past, but trillions into the future. Far beyond any human reckoning to ask where all this cooling is heading. The expansion of space is not slowing. If anything, it is speeding up, driven by something we have named dark energy, mostly so as to have a word for our ignorance. And as space grows, the old fire keeps stretching, keeps thinning, keeps cooling. The 2.7 degrees we measure today will not hold. In the deep future, it will fall to a single degree, then to fractions of a degree, then to thousandths, creeping ever closer to the absolute zero it has always avoided, but never quite arriving. The stars cannot save it. Stars are temporary. They burn through their fuel and die. The small ones fading to embers over trillions of years, the large ones already long gone. New stars form from the leftover gas, but the gas is finite, and one day the last of it will be spent. There will come a time almost incomprehensibly far from now, when the final star flickers out and is not replaced. After that, no new fire is ever lit, only the slow cooling of the old. Physicists call the end of this road the heat death of the universe, though the name is almost cruel in its irony. There is no heat in it at all. It is the state where everything has cooled to the same faint temperature, where no warmth flows because there is nowhere colder for it to flow to, where the last embers have gone dark and the universe is a uniform, freezing, silent expanse, stretched so vast that any remaining particle drifts alone, unable to find another. It is the campfire in the field, finally, completely out, and the field grown infinite. This is the direction everything is moving. Every cup of coffee cooling on a desk, every star burning down its fuel, every warm body shedding heat into the night. All of it tends the same way, toward evenness, toward stillness, toward the cold. The universe began as concentrated fire, and is spending eternity spreading that fire out until it can no longer be felt anywhere. We live in the brief, bright middle of that process, in the narrow window where there are still fires lit and still cold dark between them, still a difference, still warmth flowing from hot things to cold ones, which is the only thing that lets anything happen at all. I find I cannot decide whether that is bleak or beautiful, and I have stopped trying to settle it. The universe is cold and getting colder and will end in a dark so complete it has no temperature left to lose. And yet, right now, this very moment, there are fires everywhere, and there is a thin, warm rock with someone lying on it in the dark, listening, kept alive by the light of one of those fires crossing the freezing void to land on a sleeping world. That is rare. That is the rarest thing we know of, and it raises a question that has nothing to do with physics and everything to do with what it feels like to be a warm thing in a cooling universe. A question the cold itself seems to ask. There is a feeling that comes sometimes with all of this. People reach for words like lonely or bleak or frightening. The universe is cold, indifferent, vast beyond meaning, and we are a flicker of warmth on a single rock soon over. It can sit heavy on the chest at this hour. I want to offer a different way to hold it, because I do not think the cold is against us. It is not anything toward us at all. The void does not withhold its warmth out of cruelty. It simply has the physics it has. Heat moves the way heat moves. Space is empty the way space is empty. The universe is not a cold room that has shut us out. It is a place where warmth is rare and precious and local, and where we happen to be standing inside one of the rare warm places for a little while. There is an old idea from a writer who spent his life staring at the absurd that the only honest response to an indifferent universe is not despair but a kind of stubborn warmth, to be the thing that cares in a cosmos that does not, precisely because it does not. The cold makes the warmth mean more, not less. A fire matters because of the dark around it. A warm body matters because warmth is the exception, bought against the long cooling of everything, held for a little while before it joins the rest. And the cold, for all its reach, is slow. It has been 13 billion years undoing the first fire, and it has barely begun to finish. There are stars that will burn for trillions of years yet. There is a sun outside your window that will rise tomorrow and the day after, and for billions of mornings after that, pouring its borrowed fire across 93 million miles of freezing dark to land gently on a world full of warm and breathing things. So when you feel the cold of space, and it is worth feeling, worth letting in, try to feel the other side of it too. You are warm. Right now, in the dark, your body is a small, steady fire, holding itself at 37 degrees, against a universe that averages 270 below. That is not a small thing. It is the rarest and most temporary arrangement in all of creation. Matter gathered close enough and lucky enough to be warm, and to know that it is warm. The universe is cold because it is old and vast and emptying. We are warm because for one improbable moment, in one improbable place, the fire reached us and stayed. Both of those are true at once, the same way everything tonight has been true at once. The freezing and the fire side by side in the same dark, and on the warmest, rarest speck of it, someone is lying still in the quiet, growing heavy, letting the cold of the stars become just a thought, and then barely a thought at all. Let the whole journey settle now slowly the way heat settles out of a room at night. We began with a contradiction. Everything burning and space freezing, both at once, and we have followed it all the way down. The cold is not a force and not an enemy. It is only what remains when the fire is far away, and out there the fire is almost always far away. Heat cannot cross the emptiness by touch or by flow, because there is nothing in the emptiness to carry it. It can only travel as light, and light thins to nothing across the enormous distances between the rare, scattered fires. The universe is mostly the dark between grains of sand, and the deep cold, the floor beneath it all, is the oldest fire of all, the blaze of the early universe, stretched by the expansion of space across 13 billion years until it cooled to a whisper 3 degrees above the bottom. The cold of space is not the absence of that first fire, it is that first fire almost spent. Think, if you think of anything, of the thermos on a kitchen shelf, a small piece of engineered emptiness keeping what is warm inside it warm by refusing to let the heat travel out into the cold. You are something like that tonight. A small held warmth wrapped against a vast cold that cannot quite reach in. The same nothing that freezes the stars is the nothing that keeps your coffee hot at noon. It was never malice. It was only physics doing the one thing it does. You do not need to hold any of it tightly now. The numbers can go. The names can go. The probes, the nebula, the 2 men and their antenna full of birds. Let them drift off like heat into the dark. What is worth keeping is smaller and simpler than all of it. Somewhere out there, a star is a grain of sand, and the next grain is 400 meters of empty dark away, and between them the cold goes on almost forever. And here, on a warm speck, 2 finger widths from our own grain of sand, wrapped in a thin blanket of air that shares its heat so gently you never have to think about it, you are warm. Your body is a small fire in a cold universe, and it is keeping you right now exactly as warm as you need to be. The stars will go on burning very far away for billions of years after this night is forgotten. The cold will go on too, patient and slow and entirely without hurry, drifting between them as it always has. And none of it asks anything of you tonight. There is nothing left to work out, nothing left to hold. You can let the fire of the distant suns become just a soft idea now, a warmth you no longer have to picture. You can let the cold stay outside, where it has always been, held off by the warm air and the warm dark and the slow, steady heat of your own resting body. One last picture and then nothing, a single grain of sand resting on a fingertip in the dark. That is our sun, and every fire like it, scattered across a table too large to see the end of, with long reaches of empty dark between each one, and on a moat beside one of those grains, far too small to find, a warm and breathing thing settling now into sleep. The fires are very far away, the cold is very old, neither of them needs your attention anymore tonight. Let the grain of sand grow dim, let the table go dark. Let the warmth you are be the last thing, and then let that go soft too. The universe will still be here when you wake up. So will we. Good night.